So in this chapter, 3.4, we're looking at the zeros of a polynomial function. Remember, the zeros of a polynomial function are the x-intercepts of a polynomial graph. So our objectives is to apply the rational zero theorem, apply the fundamental theorem of algebra, apply Descartes' rule of signs, and find upper and lower bounds. Our first objective is to apply the rational zero theorem. If f of x is equal to a polynomial that has a lead term, an, x to the n, and the last term, a0, has integer coefficients and an, the lead term, is not equal to 0, and if p divided by q, written in the lowest terms, is a rational zero of f, in other words, it is an actual zero of f, then p is a factor of the constant term a0, the last term, and q is a factor of the leading term an. If a rational zero exists for a polynomial, then it must be of the form p over q, which is the factors of the last term, divided by the factors of the leading coefficient. So in this case, we're going to list all the possible rational zeros of f of x. And so in this case, we're going to look at the last term, and we see that for the last term, the potentials are plus or minus 15, plus or minus 1, plus or minus 5, plus or minus 3. For the first term, the coefficient is 4, so we have plus or minus 4, plus or minus 1, plus or minus 2, and those are our potential lead term factors. Now, I could list all the potential factors of this particular polynomial. The factors, potential factors, are 15 plus or minus 1, plus or minus 5, plus or minus 3. We could have plus or minus 3/4, plus or minus 15/4, plus or minus 5/4, and then we can go into the halves, which would be plus or minus 15/2, plus or minus 5/2, or finally plus or minus 3/2. So there are all the potential factors that could happen with this polynomial. Not all of them will work, and we would have to do the synthetic division to find which ones were. So now we're going to find the zeros and their multiplicities. The first step is to find all of the potential factors. So we have the last terms, which is plus or minus 3, plus or minus 1, and the lead term is plus or minus 2, plus or minus 1. And then the rational factors that can actually happen. So we have put the synthetic division together. We have the little box with the 2 with the coefficient of x to the 4th. 1 is the coefficient of x cubed, minus 5x squared, minus 1, and 3 are the last two terms. So now we're going to use 1. So now I pick 1 because that is that is a potential factor. So I'm going to bring a line down here. I have 2, I have 2, I have 3, I have 3, I have a minus 2, a minus 2. When I multiply, I get a minus 3, 3, and sure enough, this is a factor. So now I've got to do another possibility. So I'm going to choose a negative 1 because the last term is a negative, so we'll try a negative 1. So again, we'll bring down, we get 2, negative 2, 1, negative 1, negative 3, 3, there we go. We have a 0. And now I'm going to try one of the fractions. So I'm going to try, since I have a negative 3, I'm going to try a negative 3 halves. And when I do that, I bring down a 2. 2 times a negative 3 halves is a negative 3. And this now becomes a negative 2. And this becomes a positive 3. So now I have a 0. And now I see that it's just 1, right? Because when I bring down the 2, or actually the 1 goes up here. Sorry, made a mistake here. So I have a 2, and now I'll have a 2 here, and it gives me a 0. So here are my roots. I have 1 with a multiplicity of 2. I have a negative 1, and I have a negative 3 halves. So those are my roots for this, or the zeros for this particular polynomial. So I would like you to find the zeros and their multiplicities. I would like you to pause for this function, which is x cubed minus 2x squared minus 14x minus 5. I would like you to find the potential factors and then actually try to find what the factors are. So again, my potential last terms are plus or minus 5, plus or minus 1, plus or minus 1 again. Here, I'm going to use a 5, because I have a 5 at the end, so I'll just bring a line here. I'll bring down 1, I get 5, I get a minus 3, or no, a plus 3, don't I? So 5 times plus 3 is 15. I get a 1, I get a 5, and I get a 0. Now I notice here, this was the cubic term. Now I'm down to the squared term. I see that I have kind of an irrational situation here. So what I'm going to do is solve this one. X squared plus 3x plus 1 is equal to 0. So what I'm going to do is use the quadratic formula, because that's going to be the easiest thing to do at this particular point. And so what I do is I say, okay, x is equal to a minus 3 plus or minus the square root of 9 minus 4ac. In this case, it's just 4 divided by 2, right? So x is equal to a minus 3 plus or minus the square root of 5 over 2. So there's our roots. Our roots are, I have a 5, I have a minus 3 plus square root of 5 over 2, and I have a minus 3 minus the square root of 5 over 2. So sometimes we don't always use synthetic division completely. We may get down to a quadratic term, which may end up with complex solutions, and so that's how we find our zeros. Our second objective is to apply the fundamental theorem of algebra. If f of x is a polynomial of degree n greater than 1 with complex coefficients, then f of x has at least one complex zero. This is very important because if in fact I have a polynomial of any degree, chances are that I have at least one complex factor. So that's the most important thing, at least one, right? So the linear factorization theorem says if I have a polynomial of n degrees where n is greater than or equal to 1 and the lead coefficient is not equal to 0, then there is potentially as many factors as there are degrees, right? So in other words, what I mean by that is there are at least Cn complex numbers. Another important theorem is the conjugate zero theorem. If f of x is a polynomial with real coefficients, and if a plus bi is a zero of f of x, then its conjugate, a minus b of I, is also a zero of f of x. So the number of zeros of a polynomial, if f of x is a polynomial of degree n greater than or equal to 1 with complex coefficient, then f of x has exactly n complex zeros, provided that each zero is counted by its multiplicity. So this is probably one of the most important ideas, really, is that if we have an n degree polynomial, chances are we have exactly n complex zeros, and that includes the multiplicity. So in this problem it says given that 1 minus 5i is a zero of the polynomial f of x is equal to x cubed minus 3x squared plus 28x minus 26, find the remaining zeros and factors of f of x as a product of linear factors. Well, we were going to first divide by 1 minus 5i in synthetic division, and you will see that this is what we did, right? So when we multiplied this through, we bring down the 1. The 1 times the 1 minus 5i is 1 minus 5i. So we add the negative 3 to the 1 and we get a negative 2 minus 5i. There it is. And then we multiply that again by 1 minus 5i. And when we do that, we get a 5i minus 27. When you do the multiplication with the negative 2 minus 5i, we get the 5i minus 27, and then we add the 28 to the 27, we get 1 plus 5i, and since it's a conjugate, the middle term cancels when we multiply through, and we get a 26, and a 26 added to a negative 26 is 0. Now, since we know that the conjugate of the 0 is also a factor, we will divide through by 1 plus 5i, and when we do that we bring down the 1, we get a 1 plus 5i, and so now we have a negative 2, and we add it to 1 and we get a negative 1. The 5i's cancel, And when we hit a negative 1 times 1 plus 5i, we just get a negative 1, negative 5i, and we add those together, we get 0. So we're left with 1 minus 1. And now when we multiply 1 times 1, we get 1, and we get 0. So our factors are a 1 minus 5i, 1 plus 5i, and of course 1. And now it says a product of linear factors. So now we have f of x is equal to a x minus 1 minus 5i, x minus 1 plus 5i, and x minus 1. That's it. So now I would like you to try your hand at this one, example 5. Given that x is equal to a negative 1/2, is one solution to 2x to the 4th, x cubed plus 17x squared minus 9x minus 9 equals 0. Find the remaining solutions. So please pause and see if you can do this particular problem, and we'll come back and show you how this works. So we can see that the last terms are plus or minus 9, plus or minus 3, plus or minus 1, and the lead terms are plus or minus 2, plus or minus 1. So we were given a negative 1/2. We can divide that out into synthetic division. When we do that, we get the following result, which is a 2, negative 2, 18, and negative 18. Whenever we see groups of numbers together that rotate one after the other, like this one, 2, minus 2, 18, minus 18, we always try the root 1, and we divide that through. And when we do that, we get 2, we bring down the 2, 1 times 2 is a plus 2, the 2's cancel, we get 0, so 1 times 0 is 0, 18 comes down, 1 times 18 is 18, and we can see that the remainder is 0. Now we have a quadratic which has a complex term to it. So we set up the following. 2x squared plus 18 is equal to 0. We can divide through by 2, and we get x squared is equal to a negative 9 when we bring the 9 over. And now we have x is equal to plus or minus 3i. So our roots are negative 2, 1, and plus or minus 3i. So in example 6, we want to find a polynomial of the lowest degree with zeros of 3i and 2 as a multiplicity of 2. Because we have a complex number 3i, we know that the conjugate is also part of the polynomial. So in this particular case, we have f of x times some sort of constant a times x minus 3i, x plus 3i, times x minus 2 squared. Now we can continue on. We can expand this. We can get a times x squared plus 9. And then we have x squared minus 4x plus 4. And so the ultimate answer is, we have an a out here, obviously. That's a constant. X to the fourth minus 4x cubed plus 13x squared minus 36x plus 36. So that's the final answer for this particular problem. So in example 7, find a polynomial p of x of degree 3 with zeros 2i and 4. The polynomial must also satisfy the condition that p0 is equal to 32. So go ahead and try your luck to find at least the polynomial with the constant, and then we'll show you how to do the rest with the 32. Please pause. So in this case, we have p of x is equal to a times parentheses a minus 2i, parentheses x minus 2i, times x minus 4. We expand this, we ultimately get a is equal to x cubed minus 4x squared plus 4x minus 16. Now, with p naught, or p0 is equal to 32, is equal to the polynomial where x is evaluated at 0, and we get a times a negative 16. When we solve that, we get a is equal to a negative 2, and so now we can put it into the original polynomial function, which is p of x is equal to a negative 2 parentheses x cubed minus 4x squared plus 4x minus 16. Objective 4 is to apply Descartes' rules of signs. Let f of x be a polynomial with real coefficients and a non-zero constant term. Then the number of positive real zeros is either the same as the number of sign changes in f of x, or less than the number of sign changes in f and x by a positive even integer. The number of negative real zeros is either the same as the number of sign changes in f of x, f minus x, or less than the number of sign changes in f minus x by a positive even integer. Notice that we haven't talked about what if we don't have positive or real zeros, what if we have an imaginary zeros, and it's just the subtraction of the positive and negative real zeros that add up to the degree of the polynomial. So in this case, we determine the number of possible positive and negative real zeros. So here's what we're going to do. We're going to look at all the positive sign changes. So this is positive going to negative. There's 1. And there's 2. And there's 3. And there's 4. So the possible number of positives are either 4, 2, or 0. Now we're going to evaluate it at f minus x, and we get a negative x to the 5th minus x to the 4th, and then we put a negative x in there, we get a positive 14x cubed. That would still stay as a positive. When we put in the x squared, we can get a positive still. This is now a positive because a negative x times a negative 176 is a positive 176x plus 320. And in this case, we only see one sign change, actually. We see the sign change there as 1. So in this case, we only have one sign change, so we either have a 1, 0 here. Now, the potential of imaginary. Well, for imaginaries, we can only have 2 zeros because we can't have 4 here. We can have a 4, 1, 1 here. But then we don't have, this has to add up to 5. This has to add up to 5. And the number of real negative zeros we said was 0. So we only have the 2 possibilities in this particular case. So in this case, we have g of x is equal to 8x to the 8th minus 5x to the 7th plus 3x to the 5th minus x squared minus 3x plus 1. So in this particular case, we see we have 1, 2, 3, and 4. So we have 4 sign changes for positive. So for the positive, we either have 4 positive roots, 2 positive roots, or no positive roots. For when we have the negative, negative x, we look at the changes there. We get 1 change there, and we get a second change there. So for negative, it's either going to be 2 or 0. And then, of course, we have irrationals and imaginaries, and they can add up to 7. There can be 1 irrational and perhaps 2 complex numbers that can go along with that. So that's what we have here for this particular polynomial. So now objective 5 is to apply the upper and lower bounds. A real number b is called an upper bound of the real zeros if a polynomial, if all the real zeros are less than or equal to b. A real number a is called a lower bound of the real zeros of a polynomial if all the real zeros are greater than or equal to a. So the upper and lower bound theorem for the real zeros of a polynomial is, let f of x be a polynomial of degree n greater than or equal to 1 with real coefficients and a positive leading coefficients. Further, suppose that f of x is divided by x minus c. If c is greater than 0, if both the remainder and the coefficients of the coefficient are non-negative, then c is the upper bound for a real zero of f of x. If c is less than or equal to 0, the coefficients of the coefficient and the remainder of the alternate in signs, with 0 being considered either positive or negative as needed, then c is a lower bound for real zeros of f. So now we're going to look at the following example, example 9, and the polynomial 6x to the 4th minus 17x cubed minus 12x squared plus 23x plus 12, we're going to show that 4 is an upper bound and negative 2 is a lower bound for the real zeros. So to look at this, what we do is we're going to do the synthetic division on 4, and we get 6 minus 17 minus 12 plus 23 plus 12, and we're going to draw a line here, and we're going to do a 6, we get a 24, we get a 7, we get a 28, we get a 16, that's 64, and then when we add we get an 87, and 4 times 87, 3, 348, and when we add, we get a 360. Notice that all of these are positive, which means that this is an upper bound. And you say, well, so big deal, right? Well, what it is, what they're saying is that we won't have a root greater than 4 for this polynomial if we have rational polynomials or rational numbers that are factors of this polynomial. Then we're going to look at the lower bound. So suppose I have a -2 and 6 minus 17 minus 12, 23, and 12. We bring down a 6, we get a minus 12, we get a -29, we get a 58, we get a 46, we get a -92, we get a -69, and then we get a 138, and this becomes 150. Notice this alternates signs. So this is a lower bound. So our roots, whether they're complex or whether they're whether they are rational or irrational, they're going to be between -2 and 4 for this polynomial, the zeros. So here we're going to try and do this particular problem. You can pause it if you wish to do so. You can pause it now and wait for a few minutes and see if you can do the problem to find the zeros and their multiplicities. And we will be doing it together in just a second. So the last term is going to be plus or minus 18, plus or minus 9, plus or minus 3, plus or minus 6, plus or minus 2, and plus or minus 1. And the lead term is just going to be a plus or minus 1. Now, we're going to do the synthetic division, so we still have to worry about the factors that are not present. So for example, we have 1, but we don't have an x to the 4th, so we're going to put in 0. We have a 6, a minus 2, a minus 27, and a minus 18. Our first objective is to check to see if a 1 works, because we have a -27 and then a -18. So let's try a -1. So in this case, we'll bring down the 1. One times a -1 is 1. That gives me a -1. That gives me 1. That gives me 7. -1 times 7 is a -7, which is a -9. -1 times a -9 is 9, and that gives me 18, a -18. And this gives me 18, and there's a 0. Okay. So now we're going to go ahead and see if we can get another number out of this. I'm going to try 2. I probably could even try a -1 again, but let's try 2. So now I'm going to bring down a 1, 2, 1, 2, 9, 0, -9, right? And we still have a -18, but why do I have... Oh, that doesn't make sense. Hold on. We got this wrong, and that's wrong. Hold on. We have to get this correct. So this is actually 18, and this is 9, and then 2 times 9 is 18, and we get a 0. There is our mistake. So now whenever we have all positive numbers, 1, 1, 9, 9, we're going to try another -1. Right? This will work. We bring down a 1. We get a -1. It's a 0. That's 0. That's 9. -1 times 9 is -9. And that gives me a 0. So now we're down to x squared plus 9 is equal to 0. X squared is equal to a -9. So x is equal to plus or minus 3i. Boy, we've gotten that a couple of times. So here is our roots, a -1 with multiplicity 2. We have a 2, and we have a plus or minus 3i. So that's the end of our problem.